abstraction of a thread. So in summary, the design for a thread is this. The process is designed for protection unit by definition. Okay, the OS designer think about process as protection unit, and it's actually abstract a entire machine. And thread is for concurrent programming in modern multi-core CPU. So process is a lightweight abstraction than process. Thread is lightweight abstraction than process. The thread by definition is a execution unit, and which is abstraction of what? Of what? Which is a core. Basically a core. A single core. Okay? So that's the definition of thread abstraction. So we going through that. So thread is not protect to each other. So when setting the address space, a single process, within a single process, thread share code data stack, and having a separate stack. Okay, that's this address space static means that there's no protection between threads. That leads to lightweight creation management of threads compared to process. Okay, so which one is faster? Process creation, thread creation is fast, and process switch and thread switch, because address space is not changed, thread switch is much faster. Okay. So this is kind of summarization of process and thread, like switch overhead, protection, and process creation, sharing overhead, etc. So we going through these two designs. Okay. And then after talking about some abstractions, next time we're talking about interfaces. So POSIX thread interfaces are defined in the POSIX pip thread. The pip thread is standard API, and Windows using different thread API, which is Win32 thread API. Anyway, so mostly people using the pip threads, like talking about pip thread APIs, create, exit, join. So which is kind of similar to process create, process fork, and process exit, and process wait. Okay. So I ask you to look at textbook for understanding the examples of how to use pip thread API. Okay. Right, and because thread and process are both exist in a system, there are some kind of complicated headache issues of API handling. So for example, fork and exec is designed API for process, and thread using the different APIs. When they use, semantics has to be defined. Semantics means that, for example, when pip thread is fork or help, then what is meaning of fork? Duplicate all thread or single thread. So in pip thread implementation, because this is not kind of standard, depending on the implementation. For example, in pip thread implementation, fork duplicate only a calling thread. For this purpose, fork one system call is used duplicate one calling thread. And also exec replace entire process. If multi-thread process, if exec happens, then all threads are terminated and the process are restarted by single thread when calling exec. So these are kind of thread issues. And also the one headache issues, thread cancellation. Unlike process, thread can kill the other thread in the middle of execution, which is called thread cancellation. So a thread can sending this PID, a thread ID, by calling this thread cancel. Again, process creation requires some operation or protection, but thread has no protection. So a thread can freely kill the other thread. So there's two ways to implementation is possible to support thread cancellation, asynchronous cancellation, default cancellation. Asynchronous cancellation is terminate thread immediately, but this correct implementation of asynchronous cancellation is really hard. So people, mostly, most implementation follow this default cancellation, where the target thread is terminated at some kind of cancellation point. Specifically, the cancellation point is point that control flow, a control flow where control returns to schedule. For example, sleep, delete, idle, and someone else The fork is also cancellation point. Yes. In the fork, both threads can suspended. It goes to kernel, and parent and child process are re-entered one queue. Therefore, fork is also one of the cancellation points in thread cancellation. The pthread actually kind of do the default cancellation in the fork. Okay, so pthread both support asynchronous and default cancellation. This is also one of the complicated issues or implementation issues. Again, these issues are different from implementation. Linux and GNU thread, some other thread implementation or WinSam thread having a different semantic. You have to check it. So I give you one example on top of this POSIX implementation. Also, signal handling. Signal is concept for process concept, but if signal goes to sync or specific processes, what happens then? In case of pthread implementation, only a certain thread that's actually receiving the signal handle the signal handling. Signal handling issues. Okay, so after talking about these issues, I talk about kind of this abstraction. Developing abstraction is still ongoing research. So I giving the paper 2016 about new abstraction. This abstraction for safety and performance. Safety, I'm talking about process. Performance, I'm talking about thread. So how to design new abstraction having both benefit of protection and performance. This is the one kind of thing going on. And thread is kind of invented to address this I/O bottleneck where CPU is getting idle, even if I/O device is busy. But today, I/O bottleneck is shifted, so we kind of rethink how to address this CPU bottleneck in fast I/O era. So this is kind of way beyond the scope of this topic. This undergraduate, in the graduate operating system, we discussed this kind of thing. Okay, that's what we talked about last time. But before talking about this operating system, I want kind of recap and some kind of think about how to learn. What is purpose of learning operating system? Let's step back. Let's before jumping into details and knowledges. Let's kind of recap and rethink what we are doing now. Obviously, there are two important topics, two important things I want to get across to you throughout this semester in the course. First, design, right? Or knowledge. So, when you're reading a textbook, in general, when you start an operating system, which one do you want to focus? Which one do you kind of, what is actually the things you learned from this course? Knowledge, design idea. What is it? So kind of, listen, both are good, but what's your focus? Knowledge, design idea. Design knowledge, okay. Knowledge, design idea, knowledge. Interesting. Okay. So, before I get into this thing, do you think operating system course is the course that you memorize facts and kind of internalize it and use it? Is the operating system is that kind of subject, or some kind of course that learn some reasoning, how to apply thought, how to kind of get some high level thought to apply to solve some kind of problem, memorizing some kind of operating systems knowledge, or learn how to apply some kind of problem solving techniques for specific kind of requirement. What do you think? Which one do you focus? Memorizing? Good. I mean, just kind of sure. Memorizing, remember knowledge, or, you know, applying new idea. I just kind of listening. So now the course is kind of, almost 3 weeks past. So you guys have some kind of feeling about, what is, how to learn operating system. What is kind of meaning, what is kind of my view of studying operating system. Okay? See. So surprisingly, students have different point of view. That's the why that I can bring up two things. So first of all, most textbook, most book focusing on this. Yes, that's clear, and then you can actually kind of learn something from this course. But I put some weight for learning design idea. Yes, memorizing stuff is a good way to understand something, but operating system is kind of, is topic where when computer system comes up, how to learn complicated hardware. So that is kind of has to be main focus of one operating system, I believe, personally, philosophical. But this one is really abstract and takes a lot of time to get used to the learn design ideas. So I bring up some kind of simple ideas and mostly kind of talking about OS knowledge in the course. That's kind of limitation. But you should not miss this OS design idea. Okay? Here's the thing. Maybe these two things combined, but usually separated. Design idea is kind of the purpose and flow. Why do I talking about process first? Why do I talking about thread first? And what is kind of meaning of inventing this design? That's first part. And then we think about kind of new design. So here's kind of my perspective of learning operating system. At the beginning, there's a requirement, protection, and sharing. Every computer system, when you're designing some new systems, there's some kind of requirement you want to purchase. Hierarchy, protection. Okay, what's protection? Okay, it seems like my data is kind of not exfiltrated by others, but what does protection mean? You have to specify requirement and bring up design idea. Usually, building new abstraction and design for this abstraction. For example, process. Okay, and how to design process. During the process, how do we achieve protection, separating address space, access control resources, etc. And this design for abstraction is refined with some kind of new technology. For example, page table based protection. The hardware vendors providing page table memory management unit, embracing this new technology. Okay, and that actually kind of comes to refine protection design. That is kind of a series of steps in operating system. That's I'm talking about design like that. While performing design, you need to learn. This is my note. Okay, so summarize operating system. Then you first talking about some design ideas about underneath operating system, and you should start talking about some design ideas and refinement technologies with your operating system. That, in my point of view, that is correct way to understand operating system. So why do I emphasize this one? Let me give you an example. Is it okay to kind of, change the screen? If someone actually write down something, do it right now. I will turn that. Okay? All right. So I will kind of turn the screen. Moving on. So let me give some questions. So think about this kind of system. This is a box. It's the system you want to design. And let's say this system is game server, a web server. Web server is nothing to do with kernel. User level, pure user level software you have to develop when you join the startup. You need to build a web server. Okay? So here's the question. I want to make my web server efficient. First, there's the concept of user. Okay? This user start using my web server resource like memory and web pages. When user are connected into web server using socket, okay? In now you are web server designer. That's the first thing. How to abstract user. How to do that? I'm asking you a question. How to abstract each user. For example, as a web server administrator, you want to kill some user's connection. Sometimes, as a web server administrator, you want to throttle performance of user. You need to abstract each user. There's some way how to. IP, file. What's typical strategy? Session. Oh, getting there. Okay, good. Process, good. Process is kind of operating system's API, right? You are using the OS API by learned from OS code. OS node. Okay, their API. Okay. So, but your task is not kind of this one. This new efficient web server design. How to abstract. So, in my perspective, I say this is one connection. Okay, so I make a struct connection, or you can say session anyway, which include user ID and some kind of priority, etc. You need to abstract a user. That is one important in the perspective of managing web server. This concept. That's what I mean. Where do you learn this concept? Operating system. Abstraction. Okay. So you define this connection is a single management unit which represents a user. You think, right? Now, what do you want to do? What kind of other things you start to kind of think about this connection? Do we need to protect each other for user or not? Right? So how to model protection model in your web server? Do you really need to protect user each other or not? What do you think? What do you think? Are you serious about protection? Protection means that a user can do web server and get the connection. Within the connection, it can run user's code, user's kind of request. But this malicious user may kind of, try to hack web server. Possibly. I don't want to do that. So I want to protect. Then how to do that? Authentication is just binding a user and connection. So let's say this is Youngjin, and if Youngjin and this actually connection is represent Youngjin, that's authentication, different concept. After authenticated each connection, and I want each connection needs to be protected. How to do? How to isolate it from the OS knowledge? How to process? Map each connection as process 1. Map each connection to process 2. Map each connection to process 3. That's what you want to do. In other words, if you look at the user root, okay, yeah, protection is really important, but my web server providing internal way to isolate things. I don't want to kind of, having a strong protection between users. I want to make my web server more lightweight, less resource consuming, and spawn user requests much faster. Then what do you want to do? Right. Okay. So that's depending on your view of protection. Okay, that's designer's point of view. And if you want to, then you need to argue that, in my case, in my thought, I don't need to protection because web server has internally this kind of protection mechanisms, and we don't need to do this costly, process-based abstraction. I want, in my perspective, protection model is better. You should persuade your manager things in your reasoning. So that is kind of one simple step of system designers having through in company, in research. Okay. So that's usually what happens when you kind of going up and up as a system designer in company or researcher in any cases. Right. So looking at this claim, looking at this argument, do you think learning operating system design helps to understand this kind of view or not? What do you think? What do you think? Does it connecting that the things learning in the operating system, not just knowledge, some kind of concept, design concept like protection, how to isolate it, how to abstract it. Does it help? If you can connect these things, the things you learn in the operating system and things, the knowledge you require for designing the web server, that's my purpose. I'm trying to kind of apply this thing. Again, that is not easy for just kind of one semester course, as course designed for one semester, but throughout the course, I want to recommend to kind of having this high level point of view of design and apply to other software side. That's first I want to recommend. Unfortunately, this thing is very hard to get evaluated in the exam, right? If you can, making the exam like this one, it will be nightmare. So that's really kind of critical limitation of research, as a kind of course. But the fundamental thing you need to know is about this design knowledge first. Then acquire operating system knowledge. And more specifically, you fill the gap of your knowledge with CentOS implementation. So design idea and connecting with operating system knowledge and kind of make it more specific in CentOS implementation. The three are key pillars you need to learn the operating system course. Okay, beware of that. That's my design. That's my kind of initial intention of operating system course. Right. I want to emphasize. This is kind of this is last time I talk about these issues. But if you get familiar with learning the knowledge, you can do it. But my course is more kind of for design and knowledge and learning implementation. Okay. All right. So with this, keep this in with you know these things keep in your mind. Let's move into let's go back to this specific topic of thread implementation. Right. So thread implementation has two important keywords: kernel level, user level. So kernel level thread implementation seems natural, right? Process is implemented in the kernel. So, process PCB is implemented in the kernel for protection. But why user level thread implementation makes sense? There's no user level process implementation. There's no. I never heard about that one. But user level thread implementation, there was not. Why? Esther. But why this design makes sense? Red does not provide protection. Okay, so purely making implementation user level, okay. Process, no. Right? Why? Because user level thread implementation is much faster and lightweight. Let's move it. So let's take a look at this kernel level thread implementation. The first implementation design is kernel level, where operating system manages thread. Manage means that all thread operations, create, exit, join, cancellation, are implemented in the kernel. Okay, so therefore, the thread creation and all management require system call to like process, fork and stack. One important distinction of kernel level thread is operating system schedules all thread. Okay, thread is basic unit of execution, so basic entity of scheduling is thread in kernel level thread. Okay, so thread operating system run. Let's say this is a multi-core, core 1, core 2, core 3, core 4. Then each core running a thread. So schedule this way. However, despite of that, creating thread still cheaper than creating process because thread can share many states, but process completely isolated. Address space should be isolated, but thread is not isolated address space. So still, creating thread is cheaper. Okay, so most operating system, Windows, Linux, Solaris, macOS, the other Unix operating system follow this kernel level implementation. Specifically, this is user level. Process can contain the thread, and this is process table. Each table has process control blocks, PCB1, PCB2 table, but in any implementation they are linked to this, but maintain table, and also thread information, thread table, which is thread control block, TCB. Okay, so TCB is in the table. So traversal kernel can traverse this thread table to perform scheduling operation. So each thread information stored in the thread control block. Okay, in CentOS, there's no process control block, but thread control block actually refers to process control block. I will explain the reason there. So in CentOS, single thread system, so there's no distinction between process control block and thread control block. But in other modern operating system, process control block and thread control block are different. Thread control block is much more per thread. Process control block is per process. All right. So However, this kernel level thread implementation has limitations. They can still be too expensive compared to the approach that I'm talking about in the user level thread. Compared to this. So I will explain later why user level thread implementation is cheaper. And thread operations involves all the system calls. Okay, and kernel has to must maintain the kernel states for each thread, like this thread control block TCB. Okay, so likewise, like process, there's a we can place a limit on number of simultaneous threads to execute. Like there's kind of limitation on the maximum number of processes. Likewise, thread also has maximum number to create. Okay? And OS must scale well with increasing number of threads. So the scale we're talking about in the concurrency. So because a lot of things get compared to process only case where only few when threads are executed in the kernel, so more things to schedule in the kernel, so that it causes more kind of serial the performance concurrency problem. This is hard, and when you're learning of synchronization, when we learn the synchronization primitive, we will get back to the scalability problem later. For now, the operating system has to scale well with this large number of threads. It's one thing. And one more hassle is that kernel thread, because the implementation in the kernel, it should be general to support all needs of the needs for all programmers, languages. This is called cost of generality. For example, thread cancellation. One of the hassles for API that you need to implement. But some application does not use this, never use thread cancellation API. If application, the thread implementation in the user level, for the specific application, you don't need to implement complex functionality of thread cancellation. But once you start kind of implementing the thread in the kernel, you need to support all the possible use cases for programmers, languages, and runtime. So kernel level thread implementation is usually much bigger and less efficient than specialized user level. Okay. That's kind of cons of kernel level thread implementation. The other way is user level thread implementation. Thread is implemented at user level. What do you mean the user level? Library. Linking into thread. Linking into program. So single process thread. Where in the figure, where does thread table exist? In user level. Okay. And there is a runtime system. There's a runtime system where managing API. So therefore, when process can thread create, does it goes to kernel or runtime? Therefore, thread create API, it goes to kernel or runtime. Clearly, runtime. So this thread information is indivisible to operating system. All thread operations run PR procedure call to runtime. So creation and deletion compared to kernel and user thread implementation, which one is faster? Clearly, which one is kind of lightweight and faster? User level thread versus kernel level thread, obviously. Which one is best? User level thread implementation is much faster. Okay. So 10 to 100x faster creation time than kernel. And this is kind of, different, does not using the kernel functionality. So if you have some runtime user level library implementation, you can use the implementation in Linux and the other FreeBSD Windows in theory. Okay, so and then create a fork API for kernel, and thread API is fully implemented in user level. Okay, also tune up specialized. You can make a thread much lighter. For example, compare that TCB size, thread control block size in kernel level user level thread. Which one is likely to be smaller? User level thread TCB, kernel level TCB. Which one? Clearly, user. Because we can eliminate kernel thread implementation is the superset. User level thread implementation is subset, so much lighter. Good. Okay. So in the figure, kernel has only process table, no existence of process, and this thread information is not visible. All right, but you may wonder why modern operating systems choose kernel level thread implementation, despite of this benefit of user level thread. Why do you think? Who wins mostly? Which is a more common implementation? Kernel level. And user level thread implementation is situational, only for this case. Why do you think? Let's talk about the limitations. So here, runtime thread needs to be scheduled. So there's a scheduler. Okay? In user level thread, where the scheduler exists? Runtime kernel. Thread scheduler. Where is it? Runtime. Here. So all the thread schedulers should be implemented in user level. Timer interrupt. When you schedule, we will learn, the scheduler in the next lecture. The scheduler invoke at the occurrence of timer interrupt. But timer interrupt, does it deliver to user? Kernel. Timer interrupt. It deliver to where? Kernel. Okay. Without a special kind of take care of, thread runtime never get timer interrupt. There's a limitation. That makes kind of scheduling implementation limited, non-preemptive. We'll talk about later. So preemptive schedulers require some kind of timer-like input. Which is emulated by some timer signal. There's a way. But without that, it's very hard to implement preemptive scheduling. What is preemptive scheduling, non-preemptive scheduling? Sorry for bring up this keyword, but we will learn later in the scheduler lecture. Okay? Can user level thread run on different cores? I will get back to you soon for the question. And more important, there's critical limitation. Important. You need to kind of understand that. OS can make a poor decision as it is not aware of user level thread. This invisibility to operating system make this kind of operating system scheduler do poor decision. First, you can run a process, but that only idle thread. The process has multiple threads, but thread is idle, nothing to do. But this idle information is not visible to OS. The OS schedule a process which only having a idle thread that waste, you know, CPU cycles for learning the a process having only idle thread. That's the first thing. More significantly, blocking, understand that. Blocking the entire process when a thread initiate idle. Can you looking at this reason? Can you understand the reason why entire process is blocked when a thread initiate IO? What do you think? Okay, start getting there. Scheduler blocks entire process. Okay, finite. Here's kind of the way. User level thread process thread 1, thread 2, thread 3, and this is core 1. Okay, because scheduler is implemented in the kernel, so kernel has corresponding one kernel thread here. This is kind of scheduled in the core conceptually, and if this thread execute make use core and perform write or core, which means that this core having a write system core. It's mean. So this figure is a bit kind of confusing because in the view of kernel, this process is scheduling. This is a scheduling unit. You can think about scheduling unit. In the scheduler, and its scheduling unit is only one because process and has one schedule user one scheduling unit, and if one is make a write IO system call, this IO scheduling unit is blocked, meaning that if the other thread has to do some work, they need to be wait until this work is getting unblocked before having kind of finishing the IO. This thread has to wait. So block entire process, meaning that block the user level thread in the process when us user level thread initiate IO. That happens, which is the main reason that most OS choose kernel level. Okay, that's really serious because most processes do some small I operation, then it never exploits the concurrent execution of code. That's really bad. Okay. Another kind of subsequent problem is that unscheduled process while thread holding a lock. So this thread holding a lock, but this scheduling unit is scheduled out. Then all other kind of process waiting for lock has to wait until this thread gets scheduled and executed, holding a lock. So holding up this lock holding state are never exposed to operating systems. The operating system may choose this kind of dumb decision. So no. Okay. Most important is blocking issues. Okay. To address issue, there's some research that a blocking system call can be emulated in the library via non-blocking system calls kernel. But to do this, please take a look at this scheduler activation paper. I will not cover in the undergraduate course, but just for sure, scheduler activation. Paper. Okay, so scheduler activation, efficient kernel support for user level management for all parallelism. Parallelism what? Thread. So user level management of threads having all these blocking issues, how to make a system support for this, how to address these blocking issues. This paper is all about this. Obviously, this paper is old, 1992 paper, but great paper. So just for, if you are getting into more details of operating system, I highly recommend to read this paper, how to solve these blocking issues in the user level implementation. Right? So I will not cover in the course. So this statement is about the paper, so don't get bothered too much about your understanding details. All right. And cannot leverage multi-core CPU. Okay, so who asked the question where can user level thread run on different cores? No, because operating system only have one single scheduling unit, which is a process in user level thread, pure user level thread. So that's a problem. Okay, is the third limitation of consequence of second limitation. Third limitation is a bit more subtle. So here's thread log implementation is in the user level. If you're going to explain this one, two things. Okay, Hanlong, it's good question, but I will, let's talk about this issue after, finishing this class, so in more detail, right? So if I get into this one, I have to explain too much things to explain, okay? Good, all right, good. So limitation, okay? Clear limitation. Good performance, what is limitation? All right, so this user level thread and kernel level thread implementation actually implies this threading model. Okay, so this kernel having a scheduling entity, which is called kernel thread. Say, if user creates thread, pthread creates, then corresponding scheduling unit of kernel thread are invoked. Most popular. Okay, so again, is it user level thread implementation or kernel thread implementation? It's one term model. Kernel thread implementation, user level thread implementation, one talking about. Kernel level thread or user level thread? Which one is implementation? Kernel level. So, because of that, if this thread make a write system call, only this thread blocked. The other thread doesn't affect. So no problem happens like this blocking issue in kernel level thread. Okay, this is one form model. Typical model used in kernel level thread. The other one, merit one. There are user level threads and there are single kernel level threads. So Solaris green thread, GNU portable thread implementation use this one. So again, this many to one model. User level thread implementation, kernel level thread implementation. Okay, user level thread implementation. So if make a write system call, locked. Okay, this issue. Right? So, but again, creation happens in the user level, so it has benefit of user level implementation, but instead leads to one. So what is the remaining one? One to one, many to one. Then what? What's the remaining threading model? One to one. We talk about that. Okay? Many to many. Okay? So M and depending on configuration. So if M is likely identical to M, similar to one-to-one model, but many to M. So it allows many user level threads to be mapped into many kernel threads. Okay? So this provides for some kind of Unix using this model. So all the operating system creates sufficient number of threads. So this many-to-many model also addresses blocking issues, where one thread called write system call block and hand over to other thread and pick it. Possible. I think throughout this the KCS courses, you may experience this many-to-many threading model. Which course? Which actually use this many-to-many model? Can you guess? No way. You use it. I bet it. You already use this many-to-many threading model. What? No. Depending on the language. This language supports many-to-many model. What? No. Go? I think Go is also clear. No, C++. No, Python. I'm not sure Python is many-to-many model. Exactly. JVM here. Okay. Python is many-to-one. Okay. Good to know. I didn't know that Python is many-to-one. Java. JVM, you can create Java thread, then JVM runtime, invoke processes underneath. So JVM is typical many-to-many model. So JVM has own scheduler, okay? So which is scheduled to this user level thread or kernel level thread, and kernel level thread actually kernel level scheduler schedule this to a specific core. So JVM is typical example of many-to-many. It's the same concept of using the thread pool. No, thread pool is not the concept of this one, so it's different. Thread pool is the concept where creating thread is taking time. So pre-create the thread in the pool, but they are not actually mapping into actually running thread. For example, in many-to-many model, user level thread is for to execute, then all thread has to be executed. But in the thread pool, typically, in the thread pool, you can create like much larger number of threads, but this thread is idle even if the other if this thread is getting idle until new request to using the thread to come. So thread pool is slightly different from this threading model. And then thread pool concept of a thread pool is implemented in the high level, not in this user level and kernel level mapping. So it's different concept. Why do you use the many-to-many when still use create kernel thread expensive? Or why do you use many-to-many when you still create kernel thread? Okay, good point. So here is still, yes, but many-to-many model is good for creating number of threads. For example, some application create like 2,000 threads, but making everything into kernel thread expensive. So I see that concurrently, I only support like 10. Then you can make a 10 thread creation, and rest of thread creation happens in the user level. So many-to-many model is kind of play in the middle between kernel thread implementation and user level. Does one-to-one model mean that there's lots of kernel thread? Yes, a lot. So that is the kind of reason that why talking about West must scale well with this increasing number, right? Thread, if application thread 10,000, then kernel has to create 10,000 kernel level. Yes. So in case of kernel management, many-to-many is still small, but many-to-many is not necessarily faster than the one-to-one model because two level scheduling is required. So let's not talk about that. Any other questions? Okay. So many-to-many usually used for some kind of application having a runtime, JVM or C#. They're using many-to-many. Okay. All right. So this is last slide for the thread. So here's a kind of kind of necessarily knowledge about Linux. So this is kind of concept of threads or different implementation strategies in different kind of the library and operating system. But specifically in Linux, there is a basic unit of schedule unit called task. Okay, so the concept of task. Task is correspond to kernel threads. Okay, the corresponding concept of task. This one. Okay. Then program that only calls fork and exec, a task is identical to a process. If program is single thread, the task is identical to a process. Okay? And Linux using one-to-one model. So Linux create a task for each application thread using clone system. So let's say a process create a thread, logic thread, then go into clone system called kernel. Tasks are created in Linux, and each tasks are linked into as a linked list. So thread corresponding task, thread corresponding task. There. But one interesting feature, one interesting concept is Linux thread implementation of thread is slightly different original process thread. In original process thread, a single process that contains one and more threads. So likewise, CPU registers and user level sex and block signal mask handlers are specific to thread, and all other resources are global, shared across processes. For example, file descriptor table, heap, text, heap, data, code are shared, right? That's what you learn in the process concept. For Linux, no, not exactly. So Linux has our own implementation of Linux thread, and it is nothing but a separate task, and they may share one or more resources. The resource can be shared selectively in clone. Selectively. For example, okay, let's talk about open file descriptor. Do you remember open file descriptor in process fork and exec? So when process create a thread, the open file descriptor is shared or not shared. What we learn? Shared, not shared. And then I'll get back to your questions. Shared, right? That's concept, right? But in Linux, right? Clone fd, there is a clone files. This is flag. If clone files is set, the calling process and child process share the same file descriptor table. Now you can decipher this manual message, right? You know concept of what is file descriptor table and what is sharing, not sharing. You learned it, right? Now it's good to know that. It's good that you can actually kind of interpret these manual messages. But if it is not set, the child process inherits copy of all file descriptor opening calling processes at the time of calling. So, depending on the clone files, you can actually control that all file descriptor. For example, fork happens, and later parents open a file. Then if clone file set, then this create thread. And here open new file. this one, after create a thread, is it shared to process this thread or not, depending on this clone, this, clone file. Where's clone file? Clone file. So if clone file set, then when a process can open it, the other thread can see it. But if it's not set, no. Only before calling the process thread create, the file descriptor are shared. So file descriptor only, if it's not set, only file descriptor so far is shared. This one are not shared to across different threads. That is different semantic of POSIX thread we learned. In POSIX thread, by default, all kind of state are shared, but Linux has this controllability. That's the difference between Linux and Linux thread and POSIX thread. Okay. Likewise, clone VM. Look at clone VM. Clone VM. Sorry, clone VM. Clone VM. Clone VM. If clone VM is set, then calling process and child process run in the same address space. Is not set, they are run in separate address space, like process. So you can make some kind of combination where file descriptor shared, but address space is different. You can configure with this clone flag. Okay? All right? Do you understand what I'm talking about? Then, in this regard, Linux thread implementation is much flexible. So it has wide range of implementation is possible, including if we put all these steps, then it's identical to POSIX thread. And you can actually kind of fine-tune sharing using this clone thread. That is Linux thread model. This implementation. So Linux thread may follow the POSIX semantics, may not follow the POSIX semantics depending on the clone flag. Okay, pthread actually use these POSIX semantics when calling this clone thread. That's Linux thread implementation. All right. So this is kind of some classification of operating system. So where in single address space there are a number of threads is possible. Only one thread, multiple threads. Okay. Is it possible to multiple address space, meaning multiple processes, one process only, multiple process only? Clearly, Linux one in single address space there are multiple threads executed, and also there are multiple address spaces possible. So Linux is Linux and Windows is many systems. And one, many. So only one thread in one address space. So process and single thread. This is one, many. And you can run multiple processes. Thread one, which is traditional Unix x86. 1-to-1. No multiple process, only single process and one single thread, 1-to-1. MS-DOS, pre-early version of Macintosh. And this is embedded system. Okay, Pintos. Where? 1-to-1, one-to-many, many-to-one, many-to-many, many and many. Which one? Pintos. Where to place in Pintos? Here. Okay. Okay, so that's summarization of thread, and I think someone asked a question. Seung-jun, if process and thread are connected one-to-one, we call it single thread, and if kernel thread and user level thread are connected, then we can call it one-to-one model. Seung-jun, yes. So kernel level thread and one-to-one is different threading model, and implementation but connected. So meaning that a kernel level thread and one-to-one people think about same thing. Does does Windows have different virtual memory each? Windows having a different virtual memory each? Yes. Like Linux, in Windows, each process having a different virtual memory. Maybe. Sure. Modern Windows, not after Windows 95. Windows 3.1 is, I think, this one. Oh, no. Windows 3.1 is single process multiple. Windows 3.1. 95 after 95 here. I have a thread in Windows. I pass pointers between threads. It works. Is it different from this? No. In Windows, use a thread. So in Windows, one address space, thread 1, thread 2 are executed, like Linux. So you can actually kind of passing pointers because they are run in same address space. Oh, Windows threads having different virtual memory each? No. Same address space. Like Linux, one address space, two threads are shared address space in Windows, like Linux. Sorry, I gave a long answer. I can't visual question. Each process having a different address space, thread shared address space. Why in many colors? Like Linux. So process 1, process 2, process 3, each has one address space. So many address space. Each thread having a multiple address space can having many threads. So many to many. Many to many we can run or assign other address space to. Many means that we can assign other address space to a thread. No. That's not the case. Does operating system allows multiple address space? That's questionable. The number of address space. So does it possible to create multiple address space? For example, some of these systems does not allow multiple address space. No context switch happens. This where is this? Does not. Yes, we can think about that way. Okay, any other questions? All right. Okay, so we are talking about interesting details of threading model. So it's surprising that we just kind of simply invent a concept of thread abstraction that leads to this complicated, lots of discussions involved when implementing stuff, right? So that happens. But that's knowledge. Again, beware that with design and knowledge, we have to separate. Well, I think we have only 5 minutes, but I had to talk about this in topic. Let's quickly talking about this topic of thread. Right. Okay. Now we're changing some new topic of CPU scheduling. So far, we're talking about OS design and abstractions like process and thread. So this CPU scheduling lecture is a bit different. We will keep talking about building abstraction in the later, in virtual memory lecture, in file system lecture. We will get back to building this kind of concept of abstractions and APIs and requirements and how to build efficient abstractions. This kind of thing we learn later in virtual memory and file system. And CPU scheduling is something have different angles of design principle, design idea. Let's talk about that. For that, I'm talking about really high level. high-level thing you need to understand. Policy and mechanism. So policy. Let's see what word says. First trying to understand. Policy is about what? What should be done? Okay. It's vague. So policy is about making a decision. Policy decisions must be made for resource allocation and scheduling problems. Okay, so it seems like policy and mechanism stuff. This is kind of design term that closely has to do with scheduler. So scheduler is the thing where it contains policy and mechanism. So you can actually kind of disentangle scheduler design for policy part and mechanism part. That is the reason that I bring up these two high-level design terms, policy and mechanism. So policy seems like what should be done, and it's about decision problem, about scheduling. So specifically, this is typical policy question. What is the next process to run? This is policy question. Then, what is mechanism? Mechanism about how to do something. Policy about what? Mechanism about how. So, in a view of mechanism is tool for implementing set of policy. So this is kind of vague word, but here's kind of a mechanism question. How to make multiple process run at once? How to make a multiple process run at once? Hey, delve into these two things. Do you have a kind of sense to separate what is policy, what is mechanism, especially in the context of scheduling? Think about it. Okay, policy and mechanism. So, in the scheduler, here's the CPU. Each task job, each kernel thread are put into run queue. And this task fed into CPU and context switch out, schedule in. Get it out into a core. What am I talking about? Is it about policy, mechanism? What I'm talking about? Mechanism, policy. Then, what is policy? Policy is that scheduler asks a function which decides which task in the run queue gets scheduled, making a decision. This is what? Policy. Okay? So scheduler part is about mechanism. This part is policy. That leads to one of the most famous, most well-known design principle, which is called separating policy from mechanism. When you implement design scheduler, if you can plug them into one big function, you bet. So you have to modularize your code where this part of code function, set of functions implementing mechanism, this set of function is implementing policy. There has to be clean separation. That is most important. One of the important design principles. Separating policy of mechanism. Why? Why this design is useful? Talk about later. Okay? So scheduler is just kind of typical example for separating policy from mechanism. Policy scheduling algorithm, right? And SJF, round robin, etc. We will learn mechanism, how to manage run queue in multi-core, etc. So we learn in separate context and discuss mechanism. Mechanism part is usually short, and polish, there are lots of polishes, but they have to be separated as a modular architecture. Okay, so that's all for today, and we will going to make scheduling problem and what is the mechanism part, scheduling mechanism, and scheduling policies, and kind of other stuff about scheduling. Right? So that's all for today, and let's talk about less of scheduling stuff in this Wednesday. Okay, thank you. Talk to you next time. Okay, feel free.